In this module, we discuss how to sketch Bode diagrams by hand. In the previous module, we introduced a frequency response approach to analysis, and we discussed a few different ways in which we can represent frequency response information. In particular, we will use Bode diagrams in this course for representing frequency response information. In this module, we will learn how to sketch Bode diagrams by hand. In particular, we will learn two approaches. One approach is a point-by-point approach, and the second approach is a asymptotic approximation, where we approximate the Bode diagram of complex systems from a library of Bode diagrams of components that we've memorized. We'll then conclude with a few examples. The first approach is a brute force point-by-point approach, and so this isn't what we're going to do for the most part, but it will allow us to provide some insight into the subsequent approach that we use. It also is sort of interesting to consider because this is how a software program like MATLAB would sketch a Bode diagram. So in the previous module, we learned that we can construct a Bode diagram or find the frequency response information, specifically the magnitude and phase, by substituting s equals j omega into our transfer function. When we do that, g, our transfer function evaluated at j omega, creates a complex number. And from that complex number, we can determine the phase and magnitude of the system for that given frequency. So for a sinusoidal input of frequency omega. In particular, we get the magnitude from the magnitude of the transfer function of this complex number, where we convert it into decibels by taking the log base 10 of the number and multiplying it by 20. And then we get the phase by taking the angle of the complex number. Recall that we can find the magnitude of a complex number by applying the Pythagorean theorem. So we have the magnitude is this length, the distance of the complex number from the origin, which makes the hypotenuse of a right triangle where one leg is the real part of the complex number and the other leg is the imaginary part of the complex number. So the magnitude can simply be found from the relationship a squared plus b squared equals c squared. Similarly, the phase, or the angle of the complex number, where the angle is the distance from the positive real axis to the line drawn to the complex number. And so looking at this, we can employ the inverse tangent, where tangent of an angle is equal to the opposite side of a right triangle divided by the adjacent side of a right triangle. If you recall the sort of the mnemonic SOHCAHTOA. So the opposite side is the imaginary part of the complex number, and the adjacent side is the real part of the complex number. Again, you can basically build up the Bode diagram by substituting different values of omega, ranging all the way from small values of omega to large values of omega, plotting each point and then sort of connecting the dots. And in practice, this is what something like MATLAB would do, but we in general, if we're just trying to sketch a Bode plot by hand to get a rough idea of a system's frequency response, we won't use this approach. So the second approach that we'll learn, and this is the approach that we will use in general, is what we'll call an asymptotic approximation approach. And so the idea is that we plot straight line approximations of the individual components making up a larger transfer function. So for example, if we had something like this, we would split it up into simpler components: a simple gain, a differentiator, and a simple pole. And we will have memorized the shapes of the Bode diagrams of these sort of standard elements: gains, differentiators, integrators, poles, zeros, etc. And then it turns out that we can add the Bode plots of these individual components because of a couple of mathematical properties which I'll demonstrate. So for the magnitude plot, we know that the magnitude of a product of two complex numbers is equal to the product of the individual magnitudes of those complex numbers. And then if we go further and we take the logarithm of this, because the magnitude plot is drawn in terms of decibels, you may recall that if you take the logarithm of a product, that's equal to the sum of the logarithms. And so this property, something that maybe you remember from way back in algebra or something, this property allows us to add the magnitude plots of the individual components. So if we have a magnitude plot of a simple gain, the magnitude plot of a differentiator, and the magnitude plot of a pole, to get the magnitude plot of the whole transfer function, we simply add those individual magnitude plots together. It turns out we can do the same thing with phase. And you may recall that when you multiply complex numbers, their angles add. And a way to maybe help you remember this is to consider the complex number in polar form or exponential form. So if we consider that we have one complex number with a magnitude r1 and an angle phi1, and we multiply it with another complex number with magnitude r2 and angle phi2, when we multiply exponentials of the same base, their exponents add. And so that's one way to help you remember that the angles add. And so this property allows us to add the phase plots of the individual components just in the same manner that we added the magnitude plots. Okay. So at this point now we're going to sort of memorize a library of standard components. And the first one that we're going to start with is a simple gain, 10 or negative 10 or something. And so if we consider that we have a simple gain as our system and we feed it some sinusoidal input of some frequency omega, and think about what the output is, think about what the magnitude plot of a simple gain might look like. So k is just a number, so it just takes the sinusoidal input and it multiplies it by k. So if it were 10, then it would take the sinusoidal input and it would scale it by 10. So it would have the exact same shape, its amplitude would just be 10 times larger. And that's true no matter what frequency the input is. So the magnitude plot will be a straight line equal to 20 log k, which is the magnitude in decibels. Now consider what the phase plot would look like. So if we had k and k was equal to 10, as we said, the input sine wave would just be simply multiplied by 10. It would be exactly the same, except its amplitude would be 10 times larger. So in that instance, the phase would equal 0, no matter the frequency of the input. And so again, you would have a straight line where it would equal 0 degrees. The exception would be if k was a negative number. So what if k was equal to negative 10? Think about what the output would look like in that case. So in that situation, the magnitude would be scaled the same. But everywhere that sort of the input was positive, it would now become negative. So this peak would become a valley. The valleys would become peaks and so on. So if that were the case, what would the phase then be? It would be exactly out of phase. So it would be 180 degrees or negative 180 degrees. So the phase plot will be a straight line of either 0 degrees or 180 degrees, where at 0 degrees, if k is positive and it's completely out of phase 180 degrees if k is negative. So this is the form of a Bode plot of a simple gain, and this is something that we'll basically memorize. You can include it on your cheat sheet for the final exam or whatever if you'd like. Now let's think about what the Bode plot of a differentiator would look like. One way to sort of build some intuition about how this would work is to think about how we would plot the Bode diagram point by point. And so the way that we do that is we substitute j omega for s. So if we substitute j omega for s and think about what it looks like in the complex plane, we just have this point that's completely imaginary, no real part. And as omega changes, you could imagine how this point would move around. So for small omega, we'd have a small magnitude, and as omega increases, the point would move up along the imaginary axis. And so in that sense, the magnitude, which is the distance from the origin, increases linearly with omega. And so you get something that looks like that. And when omega is equal to 1, the magnitude is simply 1. When you take that and convert it to decibels, 20 log 1 is 0. So you get a straight line that increases with omega, and it crosses the 0 dB magnitude at 1 radian per second. And the slope of this line is 20 dBs per decade, is what we say. So for every decade increase, so for every factor of 10 increase in frequency, the magnitude increases by 20 decibels. Okay. And if we keep going, as we go to 100, it would go up to 40, 1,000, it would go up to 60, and if we go in the opposite direction, we go a factor of 10 smaller, and we're minus 20 decibels. Okay. So that's how we plot the magnitude plot of a differentiator. If we look at this figure again, and we look at the angle of that complex number as omega changes, try and think about what the phase plot would look like. So phase is the angle from the positive real axis to that point. And if you look at this, it's always positive 90 degrees, no matter the value of omega. It's always positive 90. So we get just a straight line at 90 degrees. Another way to sort of build some intuition as to what the magnitude plot and the phase plot of a differentiator looks like is to think about what the derivative of a sinusoid is. So we have some sinusoidal input into a system S, and S, the Laplace variable S in the time domain corresponds to differentiation. So we can sort of imagine what happens to the time derivative of a sinusoid as we change omega. So if we took the time derivative of this, you could use sort of the chain rule where the time derivative of the inner function omega t is just omega, and then the time derivative of the outer function, the sine, is just cosine. Okay. And so you can see that as omega increases, the magnitude of this sinusoid also increases. So the bigger omega is, the bigger the amplitude of the derivative is. Also, you can imagine, or you can sort of picture how a cosine wave is sort of 90 degrees ahead of a sine wave. And so that gives us our phase plot. Something to look at with a differentiator, which we'll come back to, is the fact that the magnitude increases. It grows very large as omega increases. And so this indicates one drawback of differentiation that we've discussed a little bit, and a drawback of using derivative control, and that is that derivatives tend to amplify high frequency noise. So if we have a high frequency input, we tend to get an amplified output. And so this is an issue that we need to be careful of, and we'll discuss it more as we go along. Now we'd like to generate the Bode diagram for an integrator. And we can generate the magnitude and phase plot in the same way that we did with the differentiator. So we can substitute s equals j omega into our transfer function. So we get 1 divided by j omega. And so when we look at this, something that we generally do with complex numbers is if we have an imaginary part in the denominator, we try and clear it out. So we multiply through, by j omega or the complex conjugate. So you get a numerator of j omega, and the denominator you have j times j. J is the square root of -1, so when you square it, you get -1, and then omega times omega is omega squared. One of the omegas and the omega squared will cancel with the omega in the numerator, and we get negative j over omega. So if we plot this in the complex plane, we have a point on the imaginary axis in a location like that. And you can think about what happens to the magnitude and what happens to the phase as we change omega, as we change the frequency of the sinusoidal input into our system. And so looking at this, since omega is in the denominator, as we increase omega, the magnitude gets smaller. The point moves closer to the origin. And so we get something that is linear, like the differentiator was, but with the differentiator, instead of the magnitude increasing with frequency, the magnitude decreases with frequency. And in fact, the slope is exactly opposite. So whereas a differentiator increased at 20 dBs per decade, an integrator decreases at 20 dBs per decade. And looking at where this line crosses the 0 dB axis, when omega is equal to 1, the magnitude is equal to 1, just equal to negative j, and 20 log 1 again is 0 dBs. So we cross this axis when omega is 1, when omega is 1 radian per second. And based on the slope, if we go forward a factor of 10, we go down to minus 20 dBs. If we go back a factor of 10, we go up to positive 20 dBs. We can also look at how the phase changes as omega changes. So looking at this, we just move along this line, and the angle to that line is minus 90 degrees. So no matter the value of omega, the phase is always minus 90 degrees. So again, we have a straight line, but instead of being equal to positive 90 degrees, we're equal to negative 90 degrees. And we can also sort of imagine this by again thinking about what division by s in the Laplace domain means. Division by s in the Laplace domain corresponds to integration. So if we have a sinusoidal input and we integrate it with respect to time, you can see that the integral is equal to minus 1 omega cosine omega t. So here again we can see that the magnitude decreases with omega, and negative cosine is always going to be 90 degrees lagging behind a sine. So our phase is always minus 90. And looking at the magnitude plot, we can get some intuition for the effect of an integrator in our system. So looking at this, for small frequencies, the magnitude gets quite large. So you can sort of imagine, the DC gain of an integrator is infinite, and this gives some intuition as to how it is that adding integral control helps to reduce steady-state error, because it results in a very high gain at low frequencies. Continuing with our process, filling out our library, the next element we're going to consider is a simple zero. And so in the same manner that we've done, we can substitute j omega for s. And we could do this sort of point by point, look at how this complex number moves in the complex plane as we change omega. So you could do that on your own. We won't do that. But just to give you a little bit of intuition, when omega is small, this term is insignificant compared to 1. So for small omegas, this behaves almost like 1. So for small omega, our transfer function is very similar to 1. And for a simple gain, the magnitude is just a straight line, 20 log of that gain. So 20 log of 1 is 0 dBs. So the magnitude is just a straight line at 0 dBs. And the phase, if you recall, as long as the gain is positive, the phase is simply 0 degrees. If we look at how this behaves when omega is large, this term will dominate the 1. This term will be very large compared to the 1, and the 1 will have negligible effect. And so if this is dominating, then it behaves like a differentiator. So for large omega, it's almost like the system is S. This is dominating the 1. It's almost as if the 1 weren't there. And so if you recall what a differentiator does, it goes up at a straight line at 20 dBs per decade. And the phase of a differentiator is positive 90 degrees. So there's a little bit of intuition. In the intermediate values of omega, when omega is not much smaller or much larger than 1, then you get in-between sort of behavior. But the way that we will approximate the Bode plot for a simple zero is in terms of straight lines. And so we'll just approximate it as a straight line at 0 for the magnitude plot, and then going up at 20 dBs per decade, and we'll make the break occur at 1 over t, where t is the coefficient in front of the s term. For the phase, the way that we'll approximate this is we'll approximate it as being 0 and then running up to plus 90, and we'll approximate this as being halfway at 1 over t, and we'll reach 90 degrees a decade after that break frequency, and we'll start to move up a decade before that break frequency. So this is maybe not the best drawing, but we're flat, then we go up at an angle, and then we're flat at 90 degrees. So this is our approximation of a Bode plot of a simple zero. In reality, it won't be straight lines like this, it'll be curved. But for our purposes, for just a simple, back of the envelope sort of analysis, this is sufficient. One thing to notice is that when we do the Bode diagrams of simple zeros, we will always put it into a form like this, and we'll call this Bode form. So we'll always switch it so that we have some coefficient multiplying s plus 1. So for example, something like s plus 3 is not in Bode form because we don't have a 1 here. So we would want to rearrange this to put it into Bode form. And by doing this, the DC gain is always 1, which is 0 dBs. So we always get this sort of behavior where we're at 0 dBs. Then we add the graphs together. We can do a similar thing for a simple pole. The properties, we substitute j omega for s, and when we have small omega, this term is insignificant compared to the 1, and so our transfer function behaves like 1 divided by 1. So for small omega, our transfer function behaves basically like a 1. So again, our magnitude plot is flat at 0 dBs. Our phase is flat at 0 degrees. And then when omega is large, then this term dominates the 1. And then it looks sort of like 1 over j omega. You know, this term is much larger than the 1, so the 1 is insignificant. So for large omega, we behave like a pure integrator almost. And so if you recall what a pure integrator does, it goes down at minus 20 dBs per decade. And the phase is a constant minus 90 degrees. And the break frequency will be just like it was for a differentiator. It'll be 1 over t. And we'll draw the phase as starting at 0 and starting to go down 1 decade before the break. So 1 factor of 10 before the break. It'll be at the halfway point at the break, and it'll finish going down 1 decade after the break. So we have a shape like that. So a simple pole and a simple zero are very similar. They're just sort of reflected over the horizontal axis in a similar manner to a differentiator and an integrator. So with a simple zero, we start out flat and then we go up at 20 dBs per decade. With a simple pole, we start out flat and we go down at 20 dBs per decade. Same thing with phase. With the differentiator, we start at 0 and we go up to plus 90. And with a simple pole, we start at 0 and we go down to minus 90. So that almost completes our library of components. The only things that we have left to examine are complex poles and complex zeros, as opposed to simple real poles and simple real zeros. But we'll discuss those in just a little bit. But now that we have our library of components that we've memorized, we can go ahead and apply approach number 2 to drawing Bode diagrams. And so this approach is, first, we put the system into Bode form. That is, put it into a form TS plus 1. We then sketch the straight line approximations of the individual components, the gains, the differentiators, the poles. Step 3, we then add the graphs, both for the magnitude plots and the phase plots based on those mathematical properties we introduced previously. This will then result in a straight line approximation of the Bode diagram of a given transfer function, and we can stop there. If we want to try and make it a little bit more accurate, we can try and approximate the curves of the true Bode diagram as opposed to just the straight line approximation Bode diagram. Okay. So here's an example. If we take a look at this, the first step is to put the system into Bode form. Looking at this transfer function, is it in Bode form? So it's not, and the reason that we can tell it's not is because it doesn't have the form TS plus 1 for that for that pole. We have a 10 here where we need a 1. And so think about how we might be able to put the system into Bode form. Basically, all we need to do is factor out a 10 from this quantity. If we do that, we factor out a 10, then we'll be left with a 1 here. We'll be left with 1 divided by 10 here. This puts us into Bode form. This 10 will then divide into that 100, giving us 10s divided by 1/10 times s plus 1. The second step is then to sketch the components. So in this case, our components consist of a simple gain, 10, a differentiator, which we'll call component B, and then a simple pole. And we've memorized the Bode diagrams of these 3 types of elements. So we'll go ahead and draw each of those. So go ahead and take a second and see if you can remember what the magnitude plot of a simple gain is. The magnitude plot of a simple gain is simply a straight line where the magnitude is equal to k, and when we convert it to decibels, we have 20 log 10, where log of 10 is just 1. So that's equal, that line is located at 20 dBs. That's component A. And we'll say the horizontal axis is 0 dBs. Our second component is a pure differentiator. So now think about what the magnitude plot of a pure differentiator looks like. So the magnitude plot of a pure differentiator is a straight line with a slope of positive 20 dBs per decade. And if you think back, the plot of a differentiator crosses the 0 dB axis at 1 radian per second. And so keeping that in mind, what frequency do you think then the magnitude plot of the differentiator component B, where do you think it crosses the magnitude plot of the simple gain? Since the slope is positive 20 dBs per decade, in order for us to rise this distance from 0 dBs to 20 dBs, we need to run, because slope is rise over run, we need to run 1 decade, 1 factor of 10. So we cross at 10 radians per second. Now let's think about what the Bode magnitude plot of the simple pole is. So the Bode magnitude plot of a simple pole starts out at 0 dBs, and then it eventually starts to go down at minus 20 dBs per decade. And the point at which it breaks is at 1 over t. And so thinking back to what our simple pole looked like, this is t, and so 1 over t is equal to 10. So the Bode diagram of the simple pole is flat at 0 dBs, and then at 10 radians per second, we break downwards at minus 20 dBs per decade. So that is component C. Okay. So those are the individual Bode diagrams of the components making up our larger transfer function. We'll then do the same thing for phase, and then in step 3 we'll add the individual diagrams of the components. And so we'll do that first for the magnitude plot before we move on to the phase. And so the way that this can be done in essence is at every individual frequency we can just sum the magnitudes to get the total magnitude. So for example, if we pick 1 radian per second as our frequency, we have one component that has a magnitude of 0, another component that has a magnitude of 0, and a component that has a magnitude of 20. So if we add the magnitudes of component A, B, and C, we have 20 plus 0 plus 0, which is equal to 20. And we can do that at all the frequencies in essence, and plot a bunch of dots and connect the dots. A more efficient way to do this is once we've sort of located a single magnitude plot for our total transfer function, we can then just sort of work based off of the slopes. So if we look at this frequency, we have two components that have magnitude plots that are flat, and one component that has a slope of positive 20 dBs per decade. So if we add those slopes together, we have a slope of 0, a slope of 0, plus a slope of 20. If you add those together, the sum of that is plus 20 dBs per decade. And if we look at lower frequencies, we maintain that slope. So if we go as omega gets smaller, these two stay flat, having a slope of 0, and component B has a slope of plus 20 dBs per decade. So this slope continues on, forever until as omega approaches 0 radians per second. In the other direction, component A stays flat, component B keeps the same magnitude, but component C, its slope changes at 10 radians per second. So we'll keep this same slope until we reach 10, and then at 10 radians per second it'll change. So above 10 radians per second we have one component that's flat, has a slope of 0, one component that has a slope of plus 20 dBs per decade, and one component that has a slope of minus 20 dBs per decade. So if you add those three, 20 plus 0 plus minus 20, that sums to 0, and we get that the slope flattens out. And so this is our Bode magnitude plot. Goes up at 20 dBs per decade, and then at 10 radians per second we level off flat. And this is versus omega in radians per second. Now we can follow a similar procedure for phase. So again, thinking back to what the phase of our individual components are, what is the phase of a simple gain? Component A is a simple gain equal to 10. So think about what its phase is equal to. So its phase plot is a straight line at 0 degrees for all frequencies. And think about what the phase plot of a differentiator looks like, component B. The phase plot of a differentiator is also a straight line, but it's at positive 90 degrees. And then finally, think about what the phase plot of a simple pole looks like this. So if you recall, a simple pole at low frequencies looks like a constant, so it starts off at 0 degrees. At high frequencies it looks like an integrator, so it goes down to minus 90 degrees. And we approximate the in-between as a straight line, where the halfway point is the break frequency, 1 over t, where 1 over t is 10, so that's the break frequency. And the phase begins to change 1 decade early at 1 radian per second, and it finishes 1 decade later at 100 radians per second. And if we connect those two lines, we get that phase plot. So this is the phase plot of component A, this is the phase plot of component B, and this is the phase plot of component C. And we simply add them together, and so again, we can go to a particular frequency and add up the phases. So at 1 radian per second and below 1 radian per second, these phases are all constant. So we have two components that have a phase of 0 and one component that has a phase of 90. So 90 plus 0 is 90. So at these low frequencies, the phase is equal to 90 degrees. At high frequencies above 100, everything's flat. So we have one component at plus 90 degrees, one component with a phase of 0 degrees, and one component with a phase of minus 90. So 90 plus 0 plus minus 90 equals 0. And the in-between we just connect by a straight line, where the halfway point is the break frequency. That's at 45 degrees. So this is the straight line approximation of the phase plot for our transfer function. Again, versus omega in radians per second. The last step, step 4, if we wish to, is to try and approximate the curves of the actual Bode diagram. So in this case, we would come up following this straight line, but in between those two straight line segments, we would have a curve. Okay, and for this one, we'd start off flat, but it would be sort of almost like an S curve. Okay. But we don't necessarily have to do that. In general, the straight line approximation is sufficient. And so that completes the Bode diagram, or the straight line approximation of the Bode diagram for that given example. In general, when you draw or sketch a Bode diagram, there's a few things, a few elements that I wish you to include in order to get full credit, and in order for people to understand the diagram that you've drawn, the important aspects of it. And so for the magnitude plot, you need to identify the frequency where slope changes, you need to identify the slope of each line segment, and you need to identify the magnitude at least one frequency. Not all frequencies, but at least one frequency. For the phase plot, you also need to identify the frequency where slope changes. You don't necessarily need to identify the individual slopes, but you do need to draw the magnitudes to be correct relative to one another. And I'll try and explain this by going back to the previous slide in a second. And then the last requirement is that the phase of the phase plot be correct as frequency goes to 0 and frequency goes to infinity. Okay, so going back to the previous slide, this is our resulting magnitude plot, this is our resulting phase plot, and so in order to be correct, we need to identify where the slope changes. So the slope changes at 10 radians per second. We can identify that by drawing a little dashed line and identifying the frequency at which that corner occurs. We need to identify the slopes. So here the slope is going up at 20 dBs per decade. We write that. Here the slope is flat, so it's apparent that it's 0. You don't actually have to write that. And we also need to identify the magnitude at least one frequency. So that's what we've done here. At 1 radian per second, the magnitude is 20 dBs. We don't need to necessarily identify where it crosses 0 dBs or the magnitude at 10 radians per second. You just need a single magnitude that sort of locates the magnitude plot. The shape is correct and you've located it vertically. With the phase plot, again, you need to identify the corner frequencies. So here, this corner occurs at 1 radian per second. This corner occurs at 100 radians per second. We don't need to identify this slope. We don't need to write it in as minus 45 degrees per decade, but we do need it to be correct relative to the other segments. So if this is flat, this needs to be shown to be going down. And if we had another break, the slopes need to be correct relative to one another, even if we don't identify the particular value of the slope. And the other thing that needs to be correct is we need to identify the phase at low frequencies and high frequencies. So in the limit, as omega approaches 0, the phase is equal to 90 degrees. We identify that. And in the limit, as omega gets large, the phase approaches 0 degrees. Okay. If we identify all of those aspects of the Bode sketch, then you'll get full credit. Okay. Now we'll go ahead and do another example. We'll now go ahead and sketch the Bode diagram of another example. And so in this case we have a second order system, but it's overdamped. Because zeta is greater than 1. And overdamped means that the poles of the transfer function are real. So we can take this quadratic denominator and we can factor it into a term s plus 1 and a term s plus 200. Okay. And so if we wanted to sketch the Bode diagram for this transfer function, the very first step is to put the system into Bode form. And from inspection, we can see that it's So in order to sketch the Bode diagram of this example, the very first thing we need to do is to put the system into Bode form. And by inspection, we can see that it currently is not in Bode form. And it's not in Bode form because of this term. We're looking for something that has the form ts plus 1, where here we don't have plus 1, we have plus 200. Therefore, in order to put it into Bode form, we need to factor 200 out. This term is okay because it's in the form ts plus 1, where t is equal to 1. So that first term is okay. We factor out a 200 out of the second term. Now the transfer function is in Bode form. The second step is you want to sketch the Bode diagrams of the components. Where in this case we have a simple gain, which is 1 over 200 if we factor it out front, and then we have two simple poles. One pole at -1 and a pole at -200. We then go ahead and sketch each of those components where we have a simple gain and two simple poles, and we've memorized the shapes of those Bode diagrams. So here again is the components of our larger transfer function put into Bode form. We'll sketch the Bode diagrams of each component separately, and then we'll add the components together. And we'll start with the magnitude plot. So thinking back to what the magnitude plot of a simple gain is, it's simply a straight line at the point 20 log k, where in this case k is 1 over 200. So 20 log 1 over 200 is approximately -46 dBs. So that's the magnitude plot of component A. We then have a simple pole, where the magnitude plot of a simple pole starts out at 0 dBs at low frequencies, and then it has a break at 1 over t, where in this case our t is equal to 1. So then 1 over t is also 1. And at that point, the slope breaks downward at -20 dBs per decade. And while we don't need to exactly identify where the two components cross one another, it's still helpful to get a rough idea. So looking at this, we're going down to -46 dBs if we go over 2 decades, 1 decade will take us down minus 20, and a second decade will take us down to minus 40. So at minus 40, we're not quite to minus 46. So 1 decade over 1 factor of 10 brings us to minus 20. Another decade brings us to minus 40. Looking at the third component, we have another simple pole. In this case, t equals 1 divided by 200. And so 1 divided by t is 200. That'll be the location of the break for that simple pole. So we start off at 0 dBs, and then at 200 we break down at minus 20 dBs per decade. That's component C. The third step in this procedure, once we've drawn the magnitude plots of the 3 individual components, is to sum the Bode diagrams. And so looking at this, at low frequencies, we have 2 components that are flat at 0 dBs and a third component that's flat at minus 46 dBs. So the slope at low frequencies is going to be flat, and the magnitude is going to equal 0 plus 0 plus minus 46. And it stays that way until we reach 1 radian per second. That's where one of our components has a break frequency. So everything is flat. Once we reach 1 radian per second, then one of the components starts to go down at minus 20 dBs per decade. So we have a component with a slope of 0, slope of minus 20, and a slope of 0, where 0 plus minus 20 plus 0 is minus 20. Therefore, the total slope is minus 20 dBs per decade. And that continues that way. So we're flat, and then at 1 radian per second we start to go down at 20, and it stays that way until we have another break at 200. And so at 200 radians per second, when we're above that frequency, component A is still flat, but now we have 2 components that are going down at minus 20 dBs per decade. So minus 20 plus 0 plus minus 20 is minus 40. And so then we'll go down even steeper. So we have something that looks like that. And if we recall the things that we need to identify, we need to identify the magnitude at least 1 frequency. We've done that here with the minus 46. We need to identify the corner frequencies. One is at 1 radian per second, the other corner is at 200 radians per second. And then we need to identify the slopes of each segment. So this segment is flat, it's 0 dBs. This segment goes down at minus 20 dBs per decade, and this segment then goes down at minus 40 dBs per decade. So it's not the best picture, but hopefully you get the idea. We then go ahead and do the same thing for the phase plot. So looking at the phase of component A, it's just a simple gain and it's positive. So its phase is a constant 0 degrees. This simple pole, it starts off at 0 degrees and ends up at minus 90. And the break starts, so the break frequency for this pole is 1 radian per second. And so we start to break down 1 decade early, and we finish 1 decade later. So we're at 0, we start to go down at 0.1, and we finish going down at 10. This is component A, this is component B. We do the same thing with this simple pole, where the break is at 200. And so 1 decade before that is 20, and 1 decade after 200 is 2000. So we start off at 0 degrees. At 20, we start to break down, and we finish at 200. That's component C. And then the next step is to sum the components. So looking at low frequencies, all three are at 0 degrees. So we sum them. We get 0 degrees. Our first break comes at 0.1, and it goes down, it continues to break down until 10. So between 0.1 and 10, we have two components that are flat and one component that's going down. Okay, and then at 10, we have 0 plus 0 plus minus 90. Goes down. And then between 10 and 20, they're both flat. All three are flat. So flat. And then at 20, one of them starts to go down again. So we have two that are flat, one that's going down, and it stops going down at 2000. And at that point, we have one component that has a magnitude of 0 and two components that have magnitudes of minus 90. So 0 plus minus 90 plus minus 90 is minus 180. Okay. And so this is our Bode diagram. We have identified the corners. We have a corner at 0.1, a corner at 10, a corner at 20, and a corner at 2000. We identify the relative slopes. So we're flat, we're down, we're flat, we're down, we're flat. And we identify the phases at low frequencies and high frequencies. So as omega goes to 0, our phase is 0 degrees, and as omega goes to infinity, our phase goes to minus 180. So that's what our phase plot looks like. Taking a look at this, let's think about what this tells us. So we have a transfer function with a pole at minus 1 and a pole at minus 200. And so based on what we know about which dynamics will dominate, this pole is much faster, the pole at minus 200. So its effect will be negligible. And it would be well approximated by something like this, with just the pole at minus 1. And if we were to graph the step responses, they would look almost identical. You'd have two step responses. They'd look very first order. You'd hardly be able to tell the difference because the one pole is 200 times faster than the other, which is quite significant. This was sort of the situation that we've seen when we looked at DC motors, where the electrical dynamics are much faster than the mechanical dynamics. So if you were to do a step response for a system like this, you would have a hard time identifying the higher order pole, the faster pole. With a Bode diagram, however, you can see both the effect of both poles. So here you can see the effect of the first pole, but you can also see the effect of the second pole. And this is one of the advantages of the Bode diagram, is that you can see the effect of higher order poles. They're not hidden. You can similarly see the effect of zeros. If we were to have a 0, you could see exactly how it affects the magnitude and exactly how it affects the phase. Okay. To finish out filling out our library of components, we now need to address complex conjugate poles and zeros. So those poles and zeros that are underdamped. And so looking at this just really quickly, we in essence have something with no zeros and two poles. And so the behavior of this system is going to be somewhat similar to this previous example. where we had a second order system, where the magnitude starts off flat, and then at high frequencies it goes to minus 40 dBs, where we get minus 20 dBs for each pole. And same thing for the phase. At low frequencies we'll be at 0 degrees, and then at high frequencies we'll be at minus 180 degrees, where we get minus 90 degrees of phase lag for each of the two poles. So we'll get a similar situation here. So the low frequencies and the high frequencies will look like the overdamped case on the previous slide. What will be different is in between the low frequencies and the high frequencies. And so in general, we'll get a Bode diagram that looks something like this. So this is the magnitude plot, this is the phase plot, and this is plotted where this point here is omega n. And so what you can see is just what we sort of predicted. At low frequencies, our magnitude plot is flat. At high frequencies, our magnitude plot has a slope of minus 40 dBs per decade, where each pole contributes minus 20 dBs per decade. And with the phase, at low frequencies, we have a phase of 0 degrees, and at high frequencies, we have a phase approaching minus 180 degrees, where each pole contributes minus 90 degrees of phase. In between, the behavior is a little different between the underdamped and the overdamped. In particular, when zeta is small, when we don't have a lot of damping, we get this sort of resonant peak here, where we get some amplification in the neighborhood of the natural frequency. You can see this sort of trend where decreasing zeta results in more resonance with more amplification. And similarly, you can see what the effect is on the phase, where the S gets steeper. So the intermediate sort of slope gets steeper with less damping. In this class, it's not necessary to exactly draw the Bode diagram of a complex conjugate pole perfectly. We just want to know basic trends. What's the behavior at low frequencies? What's the behavior at high frequencies? And what is the effect of zeta on the in-between? You know, just trends in terms of increasing resonance or decreasing resonance. Furthermore, when we have complex conjugate zeros, we have a very similar shape. It's just reflected over the horizontal axis. So this is the same sort of trend we saw with simple poles and simple zeros and differentiators and integrators. But instead of starting off at 0 and going down at a slope of minus 40 dBs per decade, a complex zero will start off at 0 and go up at plus 40 dBs per decade. And the phase, instead of going down to minus 180, will start at 0 and will go up to plus 180. So this brings us to the conclusion of Module 20. In this module, we introduce how to draw Bode plots, where we recall that Bode plots display frequency response information in two graphs, one graph being magnitude versus frequency and the other graph being phase versus frequency. We then learn two approaches for drawing the Bode diagram. One is a point-by-point approach, a brute force approach, which we in general will not employ. You calculate the magnitude of the complex number when you substitute s equals j omega into the transfer function and then convert it to decibels. And then you calculate the phase or the angle of that complex number when s equals j omega is substituted into the transfer function. And we also learned a straight line approach. And the idea is that we take a given transfer function and split it into components, simple gains, simple poles, simple zeros, integrators, differentiators, and complex poles and complex zeros. We then memorize a library of Bode diagrams for these simple components, and we draw the Bode diagram for each piece of the larger transfer function. then we add the graphs together using the mathematical properties we introduced earlier in this module.